So students, you can see a diagram on this page, and this is a common device that we have in our homes, and it is called a microwave. Now suppose some of your younger brother or sister or any layman person who doesn't have that much of idea of physics asks you that you are a student of physics. Can you explain how does this system work? How the food gets heated or cooked when it is placed in a microwave? So to understand the mechanism, to understand the very amazing thing behind this microwave, we need to understand a simple topic of physics, of dielectric materials. So we will explain this microwave with a topic, with a concept of polar materials and non-polar materials. So let us start our discussion. Hello students. So let us learn a new concept in electrostatics or electromagnetic theory, and it is related to the polar and non-polar materials. I asked you in the introductory video that how does a microwave work, because we have microwaves in our kitchens, almost all of us we have, and it cooks the food, it heats the food. So this simple application of microwave has something to do with this polarization. Now let us learn what is this all about, what is the story all about. So when we are considering dielectrics, we have generally two types of materials. One is polar material. Polar materials are those materials that have a permanent dipole moment inside them. It is due to the molecular structure. It is the built-in or inherent permanent dipole moment. And the best example is water molecule that has a inbuilt dipole moment. These materials have inbuilt dipole moment, and this is due to structure. Or you can define them, the materials in which there is a permanent dipole moment are called polar materials. These are polar substances. So what I mean to say is that in these materials, the external electric field does not induce the dipole moment. It has some other function. In the earlier section, what we saw that the induced dipole moment in an insulator, it is the external electric field, it is inducing a dipole moment. Here there is no requirement of inducing a dipole moment. The dipole moment is already inside the material. It is inherently present in the material. The best example of polar material is water, H2O. And you know the structure is something like this. H, and this is O. This is electronegative, so it draws some amount of negative charge or electrons, and this has positive charge. So this is one dipole plus charge, minus charge, and this is another dipole, and dipole moment is a vector quantity. Dipole moment is a vector quantity, and here we have two dipoles that are aligned to each other at some angle. This angle is something between something like 105 degree. So what happens, you have two vectors that are aligned to each other by some angle 105 degree, P1 and P2. Both are vectors, and these have a resultant vector in this direction. This is the resultant dipole moment. So this water molecule possesses a permanent dipole moment due to the bent structure or the asymmetric structure. The bent shape of the water molecule gives rise to a permanent dipole moment. A permanent dipole moment. So water is a polar molecule. Water is a polar molecule. In general, those materials whose molecules have an asymmetric shape like water, which is bent structure, is in asymmetric shape, the resultant dipole moment is not zero, and the material has a permanent dipole moment. However, if we consider CO2, it is a symmetric structure, straight line structure. So what happens in this case? It is a linear molecule. You have the carbon atom in between and there are the two oxygen atoms. So these are the two dipoles. This one is P1 and this one is P2. Equal and opposite dipole moments. They are oriented opposite to each other. Net dipole moment is zero. Net dipole moment is zero. So generally for asymmetric systems or asymmetric molecules have permanent dipole moment. Permanent dipole moments. Same is the case with other molecules also. You will have studied mostly in chemistry. For example, if we have CH4 methane, this CH4 is also non-polar organic material. Carbon is more electronegative than hydrogen, so it has negative charge, it has positive charge, it has positive charge, again it has positive, again it has positive. So there are four dipole moments, P1, P2, P3, P4. And all these dipole moments, they are aligned in a direction, aligned with respect to each other in the opposite manner. So the overall effect is that each dipole moment is cancelled by the opposite dipole moment. So here also the net dipole moment is zero. But in case of water, we have a non-zero dipole moment that exists inside in the material. So water is a polar molecule. Now what happens if you put a polar molecule or a dipole in the presence of an external electric field? What happens is that the electric field has certain effect on this dipole, and I think you have studied it earlier also. Let us discuss the things here. When a polar material or a polar molecule is placed in an external field, then the field, if uniform, because there are two situations, we will consider each situation. If the field is uniform, means it is same at all points in space, homogeneous. You can also say uniform or homogeneous. Then what happens? The field tends to rotate the dipole by exerting a torque, exerting a torque. It exerts a torque on this dipole and the dipole rotates. What happens is that how this torque is produced, because if you have a dipole like this is plus Q, this is minus Q, and there is an electric field E. So at each end the electric field will exert a force which is Q times C for the plus charge, and it will tend to move the plus charge in this direction, and F minus will be minus QE, which will tend to move the minus charge in this direction, and the net effect will be a rotating motion. The dipole rotates. The result is that there is a torque that acts in the dipole. Let me show you a diagram which consists of water molecules and this dipole action, rotating action of the electric field. You can see this diagram in any textbook. This is the diagram. So this, what is happening, this is the center of the dipole. This total distance is d, and these are the individual forces that are acting on the different two charges due to the electric field. Now the net torque that is produced is denoted by N. It is R plus cross F plus. F is the force QE plus R minus cross F minus. This is the net torque that is produced on the dipole, and this is Q times D cross E. So it is a vector product. If you break it, if you resolve it, it will be QD E sin theta. QD is P. So torque produced, you can also denote the torque by tau, because most of the different books use different notations. This is P, dipole moment cross E. So this is the effect of the dipole on the effect of the electric field on the dipole. If the field is uniform, so you can see here that if P and E are oriented at each other with by an angle 0, tau will be 0, and if theta is 90 degree, tau will be maximum, that is PE. Now what happens, how it is related to the microwave? Let me explain this thing in as much possible it is, because there is a derivation, and I assume that this equation you know. So what happens here, whenever you have a force that is rotating a body, or if you have a force that is moving a body, in that situation some energy is involved. Some energy is involved. So when you have a dipole in an electric field, when a dipole is placed in an external field, the energy stored in the dipole, or the energy of the dipole, is U is minus P dot E, a dot product, or it is minus PE cos theta. So if they are oriented parallel to each other, the energy is negative, most stable configuration. I will discuss this thing later. If they are perpendicular, no energy is stored. If they are oriented anti-parallel to each other, means theta is 180 degree, then the energy is positive. So for theta is equal to 0, it is minus PE, stable, negative energy, total energy negative. Theta equal to 90, energy is 0, and theta equal to 180 degree, energy is positive, so this one is unstable. And the dipole automatically, it is quite obvious that any system tries to stay in the minimum energy state for stability. So what happens in a microwave? In a microwave, the electric field, which has frequency of some gigahertz range, it acts on the dipole of dipole moment or dipole of the water molecule present in the food. Water molecule present in food. And in this situation, what happens? There is a concept of dielectric loss that I will discuss later. It is a bit complex theory. So what happens? This dipole of water, Q plus, Q minus, this dipole tends to rotate in a particular direction, and during rotation it stores this much of energy. And this energy U is equal to minus P dot E, it is used for heating the water. It changes into the heat energy and the food is cooked. This is the basic mechanism of cooking the food. Energy minus P dot E is changed into heat energy, and the water in the food boils. Water in the food starts to boil. It can take the water temperature to 100 degrees Celsius. Water in the food starts to boil. Thus, food is cooked. Now suppose if you are putting some salt in the food, that salt, suppose it is NaCl, not suppose NaCl is the salt that we use in our cooking. This NaCl is again a dipole, and this dipole also rotates and stores energy in the electric field. So there is additional amount of energy that is provided inside the food material, and it helps in cooking, because all this energy is converted into heat energy, making the water to boil and the food is getting soft. That is the thing which we call it is properly cooked. It does not remain raw or hard. The NaCl also behaves as a dipole, and stores energy. U is equal to minus P dot E, which further changes into heat energy. Further changes into heat energy that cooks the food inside the microwave. So this is the basic mechanism of microwave cooking or microwave heating inside the microwave. Although there are many complex theories, because microwave electronics is a separate branch of electronics and it is very interesting and a vast topic, so it is not the content of this course. So this is how the food is getting cooked in the microwave. Actually the microwave provides the oscillating electric field that rotates the dipole, because the electric field here is also oscillating. So there are many phenomena like dielectric loss and heat loss. That will be discussed in a separate lecture of microwave if it is possible. The high frequency electric field, rotates the dipole of water that is present in the food. Suppose you are keeping rice or potatoes in the microwave, they will get cooked. Whatever food item has water inside it, it will get cooked due to microwave effect. The high frequency electric field rotates the dipole of water inside the food, and thus it gets cooked. So this is the very important thing that we have learned today for the polar materials. In the next lecture we will do some important derivations or numericals, and we will see what happens in an inhomogeneous electric field and what is the theory of polarization in a material. How does a polarized material behave? What are the electric fields and potentials that are produced by polarized objects? Because we have understood what is polarization. So for the time being, stay tuned, watch the lecture, share, like and subscribe. We will meet in the next lecture with a new theory. Thank you.